Yeah. Hello. Let me just unmute myself and switch the camera on. And
Yeah, we have time. Don't worry.
I will try to share the screen. Let me see if it works. Okay, let me find. Can you see the screen?
Yes, we see a
Yes.
cartoon.
Yes.
Okay, 25 minutes plus 5 minutes question.
Okay. Thank you very much, Alexandro.
We track. Don't worry.
Okay, no, I will try to be on time. Don't worry. Well, first of all, I would like to thank the organizer, Professor Orfe, for the kind invitation, Nico. It's a pleasure to be presenting here at last because you have been inviting me to the tastes so many times in the past, and I was always
Muchas gracias, Luis.
Nada. So I was always having some other commitments, mostly teaching commitments, so I couldn't attend. But well, this time, thanks to the virus, this is one of the I mean, good sides of the virus that I've been finally been able to present something in the tests. And hopefully next year, if the virus permits, I will go to South Africa, and if you also invite me, I
Of
will go
course,
to
you're
South
always invited.
Africa to present my results. So let's start with my talk. I always like to include some picture in the first slide related to the place where the conference is taking place. This time, as it is taking place in the abstract world of the internet, I just decided to include a cartoon by Nico, one of his cartoons related to the tastes. This cartoon is very nice. It's a little bit eclectic in the sense that you can see at the same time uh, Isaac Newton and botijo. This is something that is rather unusual to be used to pour wine in this glass for Isaac Newton. So I suspect that this is not Isaac Newton. It's in fact Nico, who is dealing with this roasted chicken back in his hometown in Spain, right? So okay, after the fun, let me go to the subject of my talk. That is just to oh, I cannot. Let me see. Okay, now it works. Let me go to the subject of my talk. That is to convince you about the interest of looking at octupole formation, both from the perspective of a static octupole formation and also from the perspective of dynamic octupole formation, right? I will try to explain what do I mean by these two concepts, static and dynamic octupole formations. And obviously, the first thing I have to do, especially in this kind of conferences where many students are attending, is just to start trying to be pedagogic, right? So let me start talking about the two main pillars of our present understanding of nuclear structure, which are the single particle model. Well, we all know that we can understand the nucleus in terms of common mean field potential, creating orbits and placing particles on those orbits. And at the same time, we can also understand many features of nuclear structure by using ideas coming from the collective model. So deformations, rotations in space, vibrations of the shape of the nucleus, etc., etc., etc. These two pillars can be combined in just a single framework by using the mean field approximation and taking into account that the mean field approximation very often breaks spontaneously symmetries. One of the difficulties with these ideas is the fact that finally the wave function of the system has to preserve some symmetries, has to be an eigenstate of given symmetry operators. It has to be an eigenstate of the angular momentum, parity, particle number, etc. So one is forced to restore symmetries to recover quantum numbers. So all these ideas will be around in this presentation, right? But let me just, to finish this transparency, to mention that this symmetry restoration, some cases is not required because of if we are dealing with a strongly symmetry breaking regime, we can we can deal with the symmetric restoration in an approximate way. So this is what we do when we invoke the rotational model to compute quantities when we are talking, for instance, about rotational bands and things like that. Okay, so let's go to octupoles. Let's now go into the octupoles. Octupole deformation is a kind of deformation that is breaking reflection symmetry and is kind of the same kind of deformation parameters like the quadrupole deformation that we all know about, right? That is very ubiquitous in the nuclear chart. So on the left in this nice picture where we have the segregate chart with a color scheme. In this color scheme represents the deformation, quadrupole deformation of nuclei as computed using some Gogni force in the mean field approximation. And we see that most of the nuclei in the nuclear chart are quadrupole deformed. If we look at the same kind of chart, but concerning octupole deformation, we see that there are just a few nuclei that are octupole deformed, right? So this is what I mean by static octupole deformations, and the fact that there is only a static octupole formation in just a handful of nuclei table doesn't mean that the octupole correlations are not important, because in addition to static octupole correlations, we also have dynamic octupole correlations coming from symmetry restoration and fluctuations in the octupole degree of freedom, right? When we restore these symmetries, what we are doing in the old language of frames, reference frames, we are going from the intrinsic frame to the laboratory frame, and in doing so, we are generating always bands. For each intrinsic state in the intrinsic frame, by going into the laboratory frame, we are generating some set of excited states with given quantum numbers. And this is what happens, for instance, with the quadrupole deformation, where we are breaking rotational symmetry. The band generated by going into laboratory frame is a rotational band, and we have a strong E2 transitions. In the same way, when we are breaking reflection symmetry, we have octupole deformation, we are breaking parity, we have parity doublets, and we observe are strong E3 and in some cases E1 transition probabilities, right? Okay, so uh, being a little bit more quantitative, when we look at octupole formation, what we have in mind is some kind of response of the system in terms of the binding energy of the system to octupole deformation. So typically, if we have octupole deformation, we will have an energy that is depicted in this left panel, where we have a minimum at a given non-zero octupole deformation value, and we have an energy that is symmetric with respect to the exchange Q3 into minus Q3. So this energy is symmetric, right? And the deformation, I mean the density distribution is depicted also in this panel. We have the octupole pear-like shape pointing down in one of the minimum and the other one pointing up. And these two minimum are related just by a parity or transformation, just by changing R into minus R, P into minus P, we are going from this to this. So if in addition to octupole deformation, we also have quadrupole deformed states, we have rotational bands. And if octupole deformation is strong, like in this case, in the left of this plot, we have alternating parity rotational bands. If octupole deformation is less strong as before, and what do I mean by less strong? I mean that the barrier separating these two minima is lower and lower, and therefore the tunneling probability is increasing as we reduce the barrier height, right? So when the octupole deformation is less strong, the negative parity states are pushed up, and then we have this typical structure for positive parity rotational band, negative parity rotational band shifted up in energy. And finally, if there is no octupole deformation at all in the ground state, we have the same picture as before, but the negative parity states are pushed up very high in energy, typically 2 or 3 MeVs, right? So, um, okay, excuse me. Then, if we look for permanent octupole deformation, so if we look for those nuclei that show uh, uh, minima in the binding energy as a function of the octupole deformation, we find typical situations like the ones I am depicting here. In this example, I have lead 208, gadolinium 158, and radium 224. Led to OIT obviously is a doubly magic nucleus, and therefore the response to octupole formation is rather steep. The energy increases very rapidly as a function of the octupole formation. This is a typical well-defined minimum located at a reflection symmetric ground state. On the other hand, we have gadolinium 158 that is very smooth as a function of octupole deformation. So the potential energy surface is rather flat in the octupole direction. And finally, we have radium 224. That is one of the examples of octupole deformed nuclei where we have a real minimum at the mean field level at a octupole deformation different from zero. The energy gain for this minimum is typically of the order or something between 0 and 2 MeV, depending on the nucleus. And these octupole deformed configurations, as I said before, are found just in a very specific regions of the periodic table that are depicted here in this segregate chart-like plot. We have some nuclei in the actinide region. We have some nuclei in the rare earth region, and also around C equal 60. I mean, this very neutron deficient rare earth, and also in this region around zirconium, right? The reason why we only find this very specific set of nuclei showing octupole deformation in the ground state is because in order to have octupole deformation, a series of properties have to be satisfied by proton and neutron numbers. Proton and neutron numbers have to be close to what is called octupole magic numbers that corresponds to those configurations in the single particle spectrum where we have nearby opposite parity levels very close to the Fermi level. So this situation happens around particle number 34, 56, 88, 134, 196. This corresponds to delta J equal 3. And those nuclei being close in proton and neutron number to these magic octupole magic numbers show octupole deformation in the ground states. In this plot on the left, this is a calculation I made many years ago. We were only considering nuclei close to the stability line. We were not exploring very neutron-rich nuclei like in this plot on the right-hand side, where they have found other regions of octupole deformation in very neutron-rich heavy actinide nuclei and also very neutron-rich rare earth nuclei, right? The same kind of calculations have been also repeated using relativistic Lagrangians, and they come to the same conclusion. I mean, the predictions are not exactly the same of nuclei showing permanent octupole deformation, but more or less agree. Obviously, the models are different. And again, we see regions with the heavy actinides and the very neutron-rich actinides showing permanent octupole deformation. But at the end, these are just a handful of nuclei showing permanent octupole deformation. So we may wonder why it's so important to consider octupole deformation. And I said before, we have to consider dynamical correlations coming from symmetry restoration. So in the case of octupole deformation, we want to restore symmetries, right? We want to restore the parity symmetry. And the way we do is just by taking linear combinations of the intrinsic wave function, this shape, plus the wave function corresponding to applying the symmetry operator, in this case the parity operator, to the intrinsic wave function, this density on the right-hand side. So by taking the appropriate linear combinations, we end up with wave functions with the proper parity quantum number. Right? This is very simple in this case because we are dealing with a discrete symmetry. Things get a little bit more involved, like in the case Petar Marevich was considering in the previous talk, where you have to restore angular momentum, you have to deal with non-abelian continuous symmetries. Things are a little bit more involved, but in this case, dealing with these discrete symmetries is in principle very simple. So if we restore the symmetries, what can we expect? What we obtain by restoring symmetries, the excitation energy of the negative parity states with respect to the ground state, this delta A quantity. And the way we obtain it is by considering the intrinsic configurations, the mean field configurations. We project to negative parity, which is the red curve, and project to positive parity, which is the blue curve, right? And we see that there are two minima, one corresponding to positive parity, one corresponding to negative parity. Both minima are located at a non-zero value of the octupole deformation, and the energy difference between the two minima corresponds to the excitation energy of the k equals 0 or minus band. We have, in the case of this gadolinium, we have a delta E that is relatively small, just 1 MeV or so. In the case of lead-208, we have that both the ground state and the negative parity state correspond to non-zero octupole deformation, and we are gaining. I mean, we have a very large delta E. And in the case of radium-224, we have that both minima coincide. The excitation energy in this case is exactly 0. That corresponds to this limit of having a parity doublet, right? Most important is the fact that we are gaining by projecting to positive parity, we are gaining energy. The ground state is gaining some correlation energy. This is dynamic correlation energy, and is gaining this dynamic correlation energy in all the cases except for those nuclei where we have permanent octupole deformation, right? Once we restore the symmetry, we want to take into account fluctuations in the relevant parameter in this respect. That is the octupole deformation. We do it by looking at the generator coordinate method ansatz. But we take linear combinations of the intrinsic wave functions as a function of the octupole moment. I am not going to enter into the details, just to say that finally, when we do calculations in this GCM framework, we have collective wave functions. We can interpret in a very nice way, recursing to the ideas of the collective model, the physics of this system. The most important thing is that when we do this symmetry restoration plus octupole fluctuations, we take it into account, we obtain an energy gain from the ground state that is non-zero everywhere. So we have three different panels in this chart. One is the energy gain corresponding to letting the mean field to break reflection symmetry. So this is the energy gain by allowing octupole deformation in the mean field. This is the energy gain by restoring the symmetry that amounts to a non-negligible amount of energy of the order of 1 MeV, and most importantly, is not constant all over the periodic table. And when we consider fluctuations in this octupole degree of freedom, we again gain more energy of the order of 2 MeV in total. And again, the energy gain is not constant all over the periodic table. So this implies that dynamic correlations associated to the octupole degree of freedom are very important, are present all over the periodic table, and have to be taken into account if you want to understand properly binding energies and things like that. At the same time, we can also compute within this model the excitation energy of negative parity states. We can compute also B3 transition probabilities. And well, I think I'm running out of time, so I'm going to go a little bit faster. We can also improve our model, taking into account the coupling with the quadrupole degree of freedom. These are the results of some calculations I did with Peter Butler in 2000, I think, 14 or something like that, for some actinide nuclei. So you can see that the overall agreement with experimental data, with the scarce experimental data, is rather good, taking into account that we are using forces that are not tailored to describe this kind of physics. We have extended these calculations to heavy actinides. We again see that the agreement with experiment is reasonable. We also see interesting features. For instance, in the B1s, we have a dip in the B1s of the uranium isotopes, and this dip in the B1s is due to the behavior of the dipole moment as a function of the quadrupole and octupole degrees of freedom. So this is work in progress. This is something that I am working on in collaboration with Dave O'Donnell from the University of West Scotland, because they want to understand recent experimental results in this uranium-234. Right? We are also doing calculations in very neutron-rich Nobelium isotopes, where you can see this kind of funny situations where you have safe coexistence, but we have a minimum that is reflection symmetric and well-deformed, quadrupole deformed, and another minimum that is in fact the ground state that is almost spherical and is octupole deformed. So you have to consider fluctuations in the quadrupole and octupole degree of freedom in order to describe properly this kind of physics. And this is some work in progress I am carrying out in collaboration with Rainer Rodriguez. So if we want to improve our description, we have to also restore angular momentum and particle number. We are able to do this in some selected nuclei. We did some calculations for barium-244 and also for a series of barium isotopes. And the results, the theoretical results, are in reasonable agreement with recent experimental data, especially for the excitation energy of the negative parity state and the B3 transition strengths. Right? So these are the results for other barium isotopes. I don't have time, so I will go very quickly. And finally, this is what I have presented is a way to address the understanding of octupole correlations. There are other ways, like, for instance, using the interacting boson module Hamiltonian with a microscopic input. And this is the result of calculations in the radium and thorium isotopes regarding to negative parity states. We have done in collaboration with Kosuke Nomura. And this is something that has been submitted submitted for publication, and probably, hopefully, soon will be accepted. So just with this transparency, I want to finish. And I hope I have transmitted the main idea of this presentation, and is that you not only have static octupole deformations, but you also have dynamic octupole deformations. That the dynamic octupole deformations, the ones that are important, right? And important, and at the same time are present in all the nuclei, the periodic table. So thank you very much for your attention.
Thank you, Luis. Thank you for respecting the time. Since we were running late, I really appreciate it. So time for questions. You can, Peter Butler immediately. So please unmute yourself.
Yes, can you hear me? Okay. Hi, Luis. Thank you very much.
Hi, Peter.
Very interesting talk as usual. I've just got a sort of naive question, really. course, you showed somewhere near the beginning of your presentation the minimum for the negative parity states and for the positive parity state for radium-224, and said that, well, they coincide, so delta E is equal to 0. Of course, the calculations you describe, I think, have the word Bogolubov in them. And
Yes.
that means you're taking into account pairing. Now, experimentally, we don't see that these states coincide at low spin. And the naive assumption is that this has to do with pairing. But I think in all your publication, in any publication, I've only seen reference to pairing in a paper you wrote decades ago with Luis Aguido. Do you want to comment on that?
Yeah. No. I am sorry for being so imprecise in my presentation. I was running very fast. What I meant by delta E equals 0 in the case of radium-224 is the fact that you obtain a parity doublet when you are only considering parity symmetry restoration. Obviously, in addition to parity symmetry restoration, you have to consider fluctuations in the octupole degree of freedom. And once you consider those fluctuations, in addition to parity restoration, you get a delta E different from 0, right? So to say, symmetry restoration is providing you with a perfect parity doublet, but different fluctuations for the positive and negative parity states is what is splitting this doublet, and is what is probably happening in nature. I mean, in the real nuclei.
Because of pairing.
Well, because of the fluctuations. I mean, you cannot attribute those fluctuations, the different fluctuations, to specifically to pairing, right? So if we were doing calculations just without pairing, we will be obtaining exactly the same kind of effect. So it's not really pairing. What is playing a role is just the fluctuations in the octupole degree of freedom.
Okay.
Okay, we have a question in the chat from Luca Lottina. If you want to ask it yourself, or I can read it.
Let me see if I can see the
So
chat.
is there, are they nuclei with mass number 34 that have been confirmed to be octupole deformed?
With nuclear numbers around 34. Well, it depends on what do you mean by confirmed. I mean, if you mean experimentally, I think there are no firm confirmation of octupole deformation, permanent octupole deformation for those light nuclei, as far as I can tell. But obviously, from a theoretical perspective, once you have, I mean, you are confident with your interaction and you are confident with the technique you are using to assess the existence of permanent octupole deformations, I can say that it's true that there are octupole deformation there, right? So it depends on what level you want to find the confirmation, right? So experimentally, as far as I know, there's no confirmation. Theoretically, I can say it's quite clear to me that there is permanent octupole deformation in those nuclei too.
Thank you. Benjamin?
Yes, so actually I have several questions. So the first one is, did you try, I mean, are there differences between the different GONI interactions? Did you try GONI D1M, D1S, and so forth, and see there are differences on the global scale for the octupole correlations?
Well, there are some quantitative differences, obviously, but not at the qualitative level. So in one of the transparencies, I was the one where I was presenting the results with Peter Badla concerning the quadrupole octupole coupling. I was showing the results of two calculations using D1S, parametrization of the Cogni force, and D1M, which are two completely different parametrizations of the Cogni force. And the results at the quantitative level obviously differ, but not that much. But at the qualitative level, So if you look at the behavior of the excitation energies, B3s, B1s, etc., 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 as a function of neutron number, the results are pretty similar. So I would say, at least with respect to the Cogni force, and also with some results that I've seen that have been obtained with the Scherm interaction, at least at the non-relativistic level, the result seems to be quite consistent. And also, I would even dare to say that this is the case also with relativistic Lagrangians, right? So in the relativistic case, there are some other differences. You can find the phenomena are taking place at different neutron numbers and proton numbers. But I would say, I mean, the predictions are quite consistent. With they don't depend on the interaction at a qualitative level.
Okay. And okay, so my second question is, so when people talk about octupole correlation or parity correction, they always talk about Q30. Are there, I mean, do you think like other moments, Q31, 2, and so forth, will be important or
Well,
not?
probably they will play a role in some specific nuclei, but well, we have to start from the beginning, right? And the simplest thing when you are considering this kind of calculations is always to start with axially symmetric configurations. This is something that we plan to do in the future, but is computationally expensive, and also you have to take into account that we don't have a lot of computational power
Yeah, I know.
like Petamarevich, so we cannot address this kind of calculations for the moment. But it is something that is important, of course.
And finally, because I mean, it's maybe related to the previous question is, one of the previous question is, in your energy surface, you show that basically you need to include octupole everywhere, or it lowers the energy basically everywhere. Will it
Yes.
be the same with octupole, with parity and angular momentum projection? Or do you expect that part of it will be, I mean, that with angular momentum projection on top of it, you will not need to do octupole, I mean, to consider octupole as much?
No, I mean, I think octupole correlations have to be considered for binding energies for sure. And if you want to obtain a more precise description of the ground state of nuclei, so this is definitely true. So obviously, this is a kind of dynamic correlation that perhaps is not as relevant as the static correlation you obtain at the mean field level, but you have to consider it. I mean, this is the next step.
Okay.
So definitely you have to consider it, yes.
Yeah, thanks.
Okay, thanks Luis, thanks Benjamin. Other questions? I saw that Nico sent us a cartoon. I don't know if you want to comment on that.
Well, let me see if I can download it. Okay.
There are
So
many questions about the taste here and there. What is the taste? It's a school, it's a workshop, it's a seminar, it's a conference, you know. But I think Niels Bohr answered the question very well.
well, let me see. I cannot see. Okay, let me see if I can see the cartoon. Unfortunately,
I can show it to you right now.
Yeah, no, I'm having a look at it right now. So, okay, I don't know. You name it, Nico. You are the father of the tastes. So you
whatever you
name
want
it.
it to be.
No, I think it's a very nice linear combination of everything, right?
Okay.
Like Professor Bohr is saying in your cartoon.
So I think
I have to.
Yes, Nico, go on.
Well, yes, we have still a plenary talk by Dean Lee. We're going to have it at 7:15 here, so we have only half an hour. So I think we should go for a bite, no? In the meantime. And
okay, so let's thank the speaker first of all.
Thank all the speakers.
Let's thank all the speakers of this session for the very nice talk.